In this video, we'll talk about the power sum rules and how we can use them to help evaluate certain sums. So there's a few specific types of sums that we can evaluate directly, just given the setup for them. These are called power sums because, as we'll see, they involve a fixed power of the index that we're trying to add up. So the first of these is sort of the easy one. If I have the sum from k equals 1 up to n, we'll use lowercase n here, of just a number c. Well, this is c plus c plus c plus c, where I have n copies here because I start at 1, 2, 3, up to n. That means there are n copies. So the answer here is n times c. So there is one formula at the start. Adding up from 1 to n of c gets me n times c. The rest are not so simple. So if I have the sum from k equals 1 up to n of k. So this is 1 plus 2 plus 3 up to n. I want to figure out what this value is. There's a trick of figuring this out. It basically involves rewriting this sum backwards and realizing if I add vertically here, I get n plus 1 in every column. Well, that's easy. That's just n times n plus 1. And when I did this, I took my sum twice, once forward, once backwards. So my answer here is this divided by 2. So the formula you get for this, which you should know just how to use and apply the formula, is that the sum from k equals 1 up to n of k is given by n times n plus 1 over 2. In addition, there are power sum formulas for the squares and cubes of each index, which we're not going to go through how to prove, but we'll just write them out here so we can use them for future calculations. Sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. And the sum from k equals 1 to n of k cubed is n plus 1 over 2 squared. It's actually the square of the sum of just k. Let's see an example of how these come into play. I want to compute the following sum. The sum from k equals 2 to 10 of k squared minus k. An important thing to realize here is that all these formulas all had in the following form k from 1 up to n. If you don't start at 1, these formulas are no longer valid. So you have to start at 1 to make all of these work. What can I do? Well, I can write the sum of k equals 2 to 10 k squared minus k as the sum from k equals 1 to 10 k squared minus k, and then subtract the term where I plug in k equals 1. Because now I'm saying I can take the sum from 2 to 10, or I can go from 1 to 10 and then subtract off the k equals 1 term at the end. Well, this is 0, so I can just get rid of it. And now I can split this sum over the subtraction sign. So I will get the sum from k equals 1 to 10 of k squared minus the sum from k equals 1 up to 10 of k. And now I have formulas for each of these, using the n here up at the top. So what do I get? Well, I get then that the squared one is a 10 times a 10 plus 1 times a 2 times 10 plus 1 over 6. And the k one is 10 times 10 plus 1 over 2. This I will see 10 times 11 times 21 over 6 minus 10 times 11 over 2. I can cancel the 10 with a 2 to get a 5 on top. The 10 will give me a 2, and the 21 gives me a 3 to get rid of the 6. So I have 55 times 7 minus 55, which is going to be 55 times 6, or 330. So these sorts of power sum formulas can be really useful when trying to evaluate certain sums, provided we can get them into the appropriate form, where it's from 1 to some number of the power of the index. If we can do that, we can just apply formulas directly to get what these sums should be and evaluate them to actual numbers. That would take a lot of time to work out by hand if we did not have these formulas to rely on.